then I'm still paying you. I got the hard ass beats like the crack of the tech. Still paying dues. Think y'all forgot what rap sounded like? I'm still paying dues. Back to match up beats, the bang of the average. Still paying dues. I'ma make y'all pay for.
All right, again, give it up for DJ Cash. Awesome. Again, I apologize for being out of town last week. I was in London. If you watched the class video, it was bizarre. Your friend, so Cash is his old friend, Fat Face Rick, that owes you money. I was supposed to get your money. I did not get your money. He whatever, took some drugs and then walking around like the bad parts of London and like got beat up by 12-year-olds. So we had 12-year-old kids. It was super bizarre. He was fucked up. What was I supposed to do? Anyway, sorry. So I apologize for not being around. That was a weird one. That's a new one for me. Okay. So let's open this. So again, Project 0 and Homework 1 were due last night. Everyone should have completed Project 0. We're going to go over the grades later today with the TAs. And again, you have to get 100% on this by last night in order to be allowed to take the class. Project 1, we hope to release later today, and that'll be due at the end of the month, and that's going to be related to what today's class will be about, okay? The source code is not pushed yet, so everyone will have to sort of do a get pull and merge in the latest version from the main branch into your local code, okay? The other thing coming up next week on Monday and Tuesday is that we're having our visit day for all our friends in the database industry. So there's 2 days, Monday, Tuesday. Obviously the class is on Monday, but we'll duck out and teach that, and then we can always go back. So the first day was sort of research talks and some intro talks from the companies. And then on the Tuesday in the morning, that'll be these info sessions where each company will present for about an hour, talk about what their system is, what they're building, and then talk a little about internships and full-time positions as well. So that's why I posted on Piazza over the weekend or on Friday, whatever that was. So if you want to go come to these sessions, since we're having since we only have so many time slots, there will be some overlap between two companies giving the same talk or giving different talks at the same time in different rooms. So just put down what your preference is, and then we just run whatever stable marriage algorithm to generate ChatGPT to figure out the best schedule for everyone. And then if you want to, as I posted also as well, if you want to get a database job, either internship or full-time position, go to that Piazza post there, and then there's a spreadsheet. Just add yourself, what you're looking for, when you're available, and then we send that out to all our database friends, including the companies that are coming next week. So we want to get this out to them before they show up. And then we have other database friends as well. We send it to everyone else. And again, this doesn't go to recruiters, except for some rare cases. This goes to the people that are like co-founders or like VP engineering, the hiring managers for the companies. So it's not like if you go to Microsoft's website, you fill it for an internship. That's just going in the pool with everyone else. We try to skip all that and go directly to the people that care about databases. They know what this course is. Yes? The statement is, we haven't learned that much databases yet. Don't say that. Actually, here's the weirdest I've ever heard. So I know that a bunch of database companies use this class for onboarding new employees. I had somebody tell me last week in London that they were not a database person. A company wanted to interview them for a database job. And he told them straight up, I don't know anything about databases. They sent him this class to prep for the job interview. I didn't know you could do that. And he got the job. Yes. Yeah, for the advanced class, one of our projects used to be like another database company basically took it, and that was like the hacker challenge for like to hire you. They would like make you implement something that we were having you do in the class. So if you do the class, this is 721, you can show up and get hired easily. Anyway, so any questions about this, post on Piazza, and then please join us next week, okay? All right, so last class, again, it was awkward because had to teach it in the emergency room. But we spent time talking about what databases look like at the lowest level on disk. Again, at the end of the day, a database system is just a files on disk. There's nothing really special about them, at least from the OS's perspective, right? It's just as if you open up VM or Emacs, whatever your favorite editor is, and created the file, start writing data into it. That's basically what the database system is doing. And of course, how we layered the different concepts on top of each other, that sort of makes it so we can do more sophisticated things as we get further along in the semester. So today's class is now to jump ahead and say, okay, well, I have a bunch of files on disks. In order for me to do anything with those files, I got to bring them into memory. right? The classic von Neumann architecture. I got to bring the memory, and then I can manipulate them, serve queries, do whatever I want. And so today's class is really about the management or the movement of data from disk into memory and then back to disk again. We'll talk a little bit about that, how we handle dirty writes later in the semester. In this class, we'll go more detail how we make sure we do things safely to write back to disk later after the midterm. But for now, we're just trying to say, can we copy things in, and then how do we serve them up, right? And then next week, or sorry, today's Monday. So starting Wednesday, we'll actually go back down, so back to problem number 1, and talk about alternative approaches to storing data as files on disks. But the buffer pool stuff, the memory management stuff we're talking about today will still be relevant for those other design schemes. All right, so in databases, we care about, or database systems, we care about basically 2 ideas. There's two concepts that we need to be mindful of when we decide how we want to organize things on disk, how we want to bring things into memory, what algorithms we may want to use to process data or write data to disk, and so forth. So the first idea is the notion of spatial control. And that's the idea of keeping track of being mindful about where we're going to write our data on disk so that when we have to read things again, we can do so, we can try to maximize the amount of sequential access that we have. Now, I said last class that random I/O is much more expensive than sequential I/O. It's a little less of an issue in modern SSDs, but if you have any kind of rotating device, like a spinning disk hard drive, that is, there's a huge difference in the access times for sequential I/O versus random I/O, right? So that means that when we start having to write data at the disk, we want to put things that are going to be used with each other very often close to each other. The other idea is this notion of temporal control. And it's the idea here is that when we bring something into memory from disk, since that's a very expensive operation, the thing we're trying to minimize or avoid as much as possible, when we bring something into memory, we want to do as much work as we can on that data that we brought into memory before we give it up, before we release the memory or write some changes back to the disk, right? Because the worst thing to do is, like, if I got to read 3 blocks, or say I got to read 2 blocks, and I can read the first one twice and the second one once, I don't want to read the first one, do some work on it, throw it away, read the second one, do some work on it, throw it away, and then go back and get the first one again. Right? I want to maximize the amount of work I can do for every single page I'm bringing in from disk. And we'll see alternative storage models next week, on Monday next week, how you can go to town on this and avoid reading things you don't even need for queries. For today's class, we're going to mostly ignore that. So going back to that architecture I showed last class, right? At the lowest level, you have the disk. And again, this is the non-volatile storage. This is considered the permanent location of the database, the resting point of it. And then we have some kind of database file that's going to be broken up in pages. And then we said that at the beginning of the database file, or at some location that's special, we know where to find these things, we have a page directory. And this is just a sort of a database of the database pages that I have. So keeping track of, like, I want this page for this data, or sorry, for this database or this table for some file. Here's where to go find at the offset where I need it. In this diagram here, I'm showing the database is comprised of 1 file. That's what SQLite does, DuckDB does. But it could be multiple files across multiple directories, or even across multiple machines. But for now, we don't care about that. And then up above the disk, we have the volatile storage. We said this is just memory. And in this now, we're going to talk about today, the buffer pool. And this is going to be some region of memory that's been allocated, that's in the address space of our database system, that we can use to put pages that we fetch from disk into memory so that we can hand them off to other parts of the system. So in memory, when we have our buffer pool, we're going to say that the placeholders, the locations where we can store pages from disk into memory, we're going to call these frames. All right? And that's just to say that, again, just think of a giant byte buffer, and we have some offset that said that's where a frame starts, and we can put a page directly in there. Because all the pages within a single file are going to be the same size, right? These frames can be reused, and we know how to easily jump to different offsets. They're called frames because we're running out of words. We already have pages. Sometimes it's called blocks, right? We don't call them a buffer because the whole thing is called a buffer or cache, right? So we're calling them frames because that's all we got. So then we have an execution engine, and again, so this thing is where we actually execute queries. And as it's running, somehow it says, I want to read some data, and it's in page 2. Doesn't know where page 2 is, but it knows to talk to the buffer pool manager, and it exposes an API that allows you to go get page 2. So in order to figure out what page 2 is, we got to bring the page directory in. I'm showing you this as a sort of separate step. In actuality, when the system boots up, you usually load that in the very first thing you do because you need to know what's in there. But for now, it's fine. We're just showing it as a separate step. Then now we can select the page directory, and then that tells us where we want to find page 2. We find a free frame in our buffer pool where we just copy that page from disk into memory. And then now we hand back the execution engine a pointer to that page in that frame. And the guarantee that the buffer pool manager is going to provide for the rest of our system is that if we go tell this execution engine, here's the pointer to the page that you wanted, that pointer will be valid until that execution engine or whatever asked for that page comes back and says, I'm done with it. We'll talk about how we do that in a second. Now, the cool thing about the buffer pool manager is that we can actually reorder and change the location of a page any way that we want if we have to bring it in multiple times. So let's say now we run some kind of eviction policy. We decide that we want to throw away page 2 to free memory. Realize we have a free space. We would have kept it, but we can ignore that. So then now if the execution engine comes back and says, hey, I want page 2 again, the buffer pool manager recognizes that it doesn't have that page in memory. It's got to go back to disk and get it. But now it's going to copy into this frame. And it hands back that pointer to the database system, to the execution engine. And that's perfectly fine. Right? It's just an address in memory telling you here's where to go find the thing that you wanted. What's that? The question is, what about the previous pointer going back here? So at some point when we hand off this pointer, the contract is, I'm giving you this memory. You got to tell me when you're done with it. So at some point, the executioner says, oh, I'm done with it. That's why we were allowed to then evict it. What's that? The statement is something like reference counting. Yes, but we'll get there in a second. But there's more. Yeah. The question is, what if the execution engine asks for more frames that are in memory? We got to throw things away. We'll handle that. Right. The whole point is, like we said at the beginning, we want to give the illusion that we have more memory than we actually do. So we'll have to handle that ourselves. Other questions? Yes.
Is it random how the frames are being selected, or is there optimization even in that?
The question is it random how the frames are being selected by the execution engine or for eviction?
No, when the second time you showed that the page 2 loaded onto the second frame.
How do we decide to do that frame? We'll cover that in a second. But we want to write the rest of the system, the execution engine, so that we don't actually care. It could be random. Who cares? You asked me for this page. Here's the memory for it. Go for it. Yes?
The size ratio of page to frame is 1:1.
The question is the size ratio from a page to frame 1:1? Yes, it has to be. And we'll talk about it. Like there are some advanced systems like IBM DB2 where you can actually have a buffer pool that has different page sizes per table, per index, right? And you can even specify what the replacement policy should be per buffer pool instance. But in general, like if it has to be like if I'm reading from this, I know I'm reading from this database file on disk, it's organized in these database page sizes. My buffer pool has to have frames of those sizes. Okay. So I'm showing this example here that we're using the buffer pool to read disk pages or the data pages for a database. But in actuality, we're going to be using these buffer pools for all the different parts of the database system. Basically, when the system boots up, when the database system boots up, you want to call malloc, get all the memory you're going to ever need to run queries, and then you're done. You never want to go back to the OS and get more memory. Not every system does that. But in general, that's what you want. That's the ideal case. Because the worst thing for me to do is start to try to outdo a malloc and get some memory I need for like a temp buffer, and then the OS says, I'm out. Right? You want to know that sooner rather than later. So in general, anytime you're going to allocate memory, not from the stack, but anything from the heap for your application or your data system, you want that to come from one of these buffer pools. Some of them will be backed by disk, meaning like if I, as you were saying, if I'm trying to allocate more memory than I actually have available to me, it can spill to disk. Other times you don't want to do that. Like if you just say, if I'm out of memory, then I'll just kill the query, right? So again, we won't really talk about these right now. We'll talk about, when we talk about join algorithms and sorting algorithms, this make more sense, log buffers as well. Just be aware that there's memory being used for other things other than just tuples or indexes. But the main one we want to focus on is those things. All right, so today we're going to talk about the basics of what a buffer pool manager is. I think the textbook calls them a buffer cache or buffer cache manager. Sometimes it's called a buffer manager. They're all basically the same thing. It's managing the memory that the data system is going to use to run queries. Then we'll talk about my pet topic of why you don't want to use the operating system for any of this, because it's going to ruin your life. And then we'll talk about replacement policies, how to decide when we want to evict things, how to write things out to disk, and then do some additional optimizations. Okay? All right, so the buffer pool, as I said, it's just a bunch of memory that we've allocated in our data system that we're going to use to put in fixed size pages. And those locations within that giant array is going to be each location where we could put a page in, we'll call that a frame. So again, when now the data system, other parts of the data system says, I want to get this page, it asks the buffer pool manager for it. If it's available, if it's already in memory, then the buffer pool manager just hands back the pointer for it. If it's not available, then it has to decide what frame to put it in. And if there's not a free frame, we'll have to handle that. And the page you're putting into memory that you're going to hand off to the other parts of the system, it'll be an exact copy of what is given, what is being read into from disk. Right? There isn't like, let me make sure this is true. If the low level of say you're using a storage appliance, it might do its own compression down below actually the hardware level. But when you actually do a read against that file, you're going to get back the uncompressed bytes, and that's what the data system is going to hand back to the exchange engine. Now, within that page, it actually may be compressed, and the data system knows how to interpret that compression. We'll see how we do that next week. But in general, it's a one-to-one copy for whatever's on disk goes into memory. So if we look at an example like this, we have 4 pages on disk. We want to read page 1. The buffer manager is going to say, all right, I got to put this somewhere. It picks the first frame, it makes a copy into it in there. All right. Now, once we read page 3, same thing, make a copy and go in there. So the buffer pool is actually the memory location of where we actually store this. There's an additional data structure called the page table that's going to sit in front of this memory, which is actually the entry point for how you find pages that are in memory or not, or check whether they're in memory or not. I think it is just another hash table where I do a lookup on the page ID, and then within that slot, within that hash table, it's going to tell me whether the entry exists or not and where to go find it. So there's some additional metadata in here, sort of what they brought about, like reference counting. Where I'm also going to keep track of like how many times have I handed out this page to other parts of the system. It's called a pin counter, reference counter, same idea. And so you would say a page is pinned in memory means that some other part of the system currently has a pointer to that memory, and therefore I don't want to free that frame up and throw away whatever's in there, because I don't want some other part of the system start reading interpreting what's inside the page, and then I replace it with another page, and now it starts getting garbage data or incorrect data. So the pin counter is how we're going to avoid that problem. We also can maintain a latch inside our data structure to ensure that while we're doing a lookup in the page table to say, does this, yes, question, yes. The question is what, sorry? The question is, what are page table entry sizes? Less than a kilobyte, right? Because the big part is the actual frames, the actual memory. The hash table can be large in terms of having a lot of entries, but each entry itself is not that big, right? Like, so there'll be like a dirty flag where it's been modified. That's 1 byte. The reference counter, probably a single byte. Access tracking information, that would be like what transaction is actually is accessing this for me, like what is the thread or the worker ID that actually holds the pin for this. Again, it's not that big. All right, so I need a latch within my my page table as well, so that like if I say, all right, well, I need to go get page 2, I have a free location in my page table. Let me protect this while I go then do the disk read to go put that into a frame to ensure that nobody else comes along and tries to put something in my page table that same slot, that same location. Right, and then once I'm done, I can release the latch and throw away the pin. Anybody know what a latch is? Go for it. Mutex, perfect, yes. So if you're coming from the OS world, what we call latches, they'll call locks. And at the end of the day, it's a mutex. You could use the OS's mutex or the pthread mutex. You shouldn't, but you could. We can always do better in the data system. But the reason why we have the distinction between locks and latches is that locks in the database world is a separate concept that is about protecting higher level logical entities. Like I can lock a page, I can lock a tuple, I can lock an index, right? And a latch is going to be what you protect an internal critical section of any kind of data structure inside your database system from like multiple threads or multiple workers accessing it at the same time. And the reason why we have to make this distinction is that in the lock case, we have to deal with stupid people on the outside of the database system. Like someone starts a transaction and then decides to go out, for a cup of coffee, and then transaction's still open. So we, as a data system, have to deal with somebody, walking away from the computer and be able to rectify any issues like deadlocks or live locks and so forth. A latch, since that's protecting internal data structure, that's us, like who are actually building the data system. We're paid a lot of money to do it, and therefore we won't be stupid, in theory. And therefore it's up for us to make sure that we don't have deadlocks or other problems. Like, because there isn't going to be this lock manager thing up above that's going to kill us if we have deadlocks. So it's up for us to make sure we do this correctly. So this would be a low-level mutex. You could use the, again, pthread mutex, the Apple one called the parking mutex one, or parking locks. That's better. But we'll cover that in a few more weeks. But the main idea here is that it's going to protect the internal data structure of the system, right? And there isn't going to be anybody that can make sure that we don't have problems. And there's not going to be any way to roll back changes unless we do it ourselves. In the case of a lock, if I open a transaction through SQL and then I make some changes and then my transaction gets killed, the database system will clean up the mess afterwards for me. It won't do that for a latch. Again, just also as a reminder between the page table and the page directory. The page directory is that thing I said in the beginning where I use that to find the pages I want on disk, given an ID. And the page table is this ephemeral internal data structure that keeps track of, here's the location within frames of all the pages that I brought in from disk and where they reside in memory. Again, you don't have to store that on disk. If you crash, you lose whatever's in memory anyway, so who cares? There are some systems that actually will write out what the contents of the page table is, so that if I crash and come back, rather than sort of organically populating the page table through whoever accesses what, I can actually preload or prefetch all the pages that I had in memory before after the crash and bring that back in. You see this in serverless systems. Again, we'll cover this later, but just in general, the page table does not need to be durable, does not need to be stored on disk. All right, so what does this sound like what I've been talking about so far? He sort of brought up the point before where what happens if I have, my database is large amount of memory that I have. We're basically, again, trying to provide the illusion that our system has more memory than it actually physically has. What does that sound like? Is it swapping? But like, what is the higher level concept of that? Virtual memory, yes. All right, well, yeah, if you take an OS class, this is what the OS wants to do for you through virtual memory. And it has a mechanism called memory map files that allows you to take a file that resides on disk and you call mmap open on it, and it basically maps the contents of that file into the address space of your process. Right? It obviously doesn't do this eagerly, it does this lazily. So I call the open on the file, and it then gives me a starting point of the memory address. And anytime I jump into an offset within that starting memory address, it will correspond to some offset within the pages of the file that I mapped in. So the OS was going to be trying to do this. Basically, we're trying to do the same thing we're talking about today, but it's going to do a terrible job at it. I guess I'm sort of poisoning the well already, but trust me, you don't want to do this. All right, so here's that file we had on disk before, and we have virtual memory. So again, I call mmap on it, and then in my address space, my process, I can say, all right, well, here's the 4 pages starting at some offset for the file that you mapped in. So then now when any thread or process accesses one of these pages, right, you try to, again, just read a memory address at one of these offsets. The OS says, oh, well, the thing you want isn't actually in memory. It's a major page fault, so it pauses your thread, then fetches whatever the page you wanted, puts it into physical memory, and then wires up the virtual memory table to now point to that physical memory. And then your process gets control back again, and you can do whatever you want with it. All right, read another page, same thing. Right, it's not in memory. We get a major page fault. We block, fetches it in, we wire it up, and then our process can run again. So now the challenge is going to be what happens when we try to access something again for this file, but now we're out of physical memory, right? What's going to happen? I've already said, right? It's going to block your process. Then it's going to go decide now which page in physical memory to evict. If it's not dirty, it just throws it away. If it is dirty, meaning it's been modified since you've read it in, it'll write it back out to disk. Then copy whatever the pages that you wanted in once it's put in the physical memory, and then hand you back control. So again, this seems like exactly what we want in our database system, but because the operating system is doing it for us, it doesn't know anything about SQL, doesn't know anything about queries or transactions or whatever we're trying to do, doesn't know anything about what actually is in these files, and therefore it's not in a good position to make decisions about what the right thing to evict is. So what are the problems? So the first thing is that the OS can decide to swap out a dirty page anytime that it wants, right? The background writer can go through and says, all right, you've modified this page, so let me go ahead and preemptively write it out for you so that at some point, if I need to evict it, I don't have, and since I'm installing your process, I don't have to block you for a long time while I write it out. I can do this in the background, and that way when you want to go evict this, you just can throw it away because it's now been marked clean. But the problem is we have no control, we being the database system, have no control of what it's going to write out and when it's going to write it out. Because again, it doesn't know what's in these files, doesn't know how the upper level part of the transaction is actually modifying them. So there may be a case where there's a dependency between multiple pages where I can't write out this dirty page until this other dirty page has been written out. Again, we'll see this when we talk about transactions later on, but like, you basically, if I modify a page in the data system, I want to make sure I write a log record that says, here's the change I made to this page before I write out that change. But the OS doesn't know that, there's a write-ahead log or this other thing over here. It says, all right, I got some dirty pages, let me go ahead and write them out. You can prevent them from being evicted using mlock, which is basically the same thing as a pin for the pages, but that doesn't prevent it from running it out. Right? So that's a problem for us. Then we have this stalling issue where the data system doesn't know what pages are in memory. It tries to go then access something. And if it's not memory, then my worker, either a thread or process, will have to stall while the OS decides to go fetch it in. So that means now my worker is not actually doing any useful, any useful work that it could be doing while it's going fetching something from the disk in the background because it got blocked. Now you could start, doing a little play a little game where you have a separate thread on the side that can go touch a page that you think you're going to need, and that way, if it gets blocked, the worker that's running the query can still do other stuff. But then you're adding more complexity to your system when what the OS is trying to do, trying to make it simple, trying to do something simple for you. But now you're actually adding a bunch of stuff in order to deal with the OS doing stupid things for you. Another big problem that's actually more nuanced and not really obvious until you actually start building real systems, is that error handling becomes more challenging now with the OS, with mmap, because a failure can occur at any time, anywhere in your application or in your system. That means that at any time I'm touched that memory, it might have got evicted, or there might be a problem in the actual underlying hardware, and I'm not getting an exception. I'm going to get an interruption or interrupt. So now I've got to have interrupt handler code all throughout my system. Whereas if I was managing disk and memory myself in my database system, at the time I try to go read it, if I can't read it and I get an error, that's the only location where I need to handle that. But if you use mmap, because it's again trying to be transparent to you, it's all over in your system. Yes.
I'm confused what would cause the need for a page fault handler, because I would think if there's a page fault, just because the page is not physical memory, the OS will take care of that for you, right? You'll have to handle that.
So it's not a page fault. It'd be like an interrupt, like the disk is broken or something. Yeah. So you try to read something and someone ripped the file out. It's gone. What do you do? Or rip the hardware out. You get an interrupt. The question is, statement is, and they're correct, that like if someone screws around the system and starts breaking your files, but the point I'm trying to make is like, if I say I read something from disk, I put it into memory, and then I rip the hard drive out. then in theory, the system can still run because it has it in memory, right? And so if I then try to read that page again, since the file's gone, I'll get a failure at that moment, and I can handle it right there. Whereas with mmap, if some other part of the system tries to read it again, and since it's trying to be transparent to me, I just do a memory access.
Okay, so it's like
Non-deterministic, yes. And it's a bunch of more engineering work you have to do. And the last one, I won't belabor this too much, but just sort of take my word on this. It's going to be slower than doing everything ourselves, because how's the OS tracking virtual memory? It's the same thing as the page table that we had before. So it's going to have its own internal data structures with its own latches it used to protect those things. And we in the data system world, we can always do a better job. So again, I don't want to go to this too much, but saying like you can start tricking around the OS to make it look more like what we actually want to build in our database system, but it's just as much work. And in the end, you're relinquishing control to what's being brought into memory and when it's being written out, at what time and when. Like all that is you're giving up to the OS, and you're just better off just writing everything yourself, which is what this class is about. So there's a bunch of systems that have been tried to use mmap over the years. Probably the one that you're most familiar with is MongoDB. Right? When MongoDB first started, they didn't have their own buffer pool. What we're talking about today, they relied on mmap, right? But since then, all these systems have gotten rid of it because they basically realized all the mistakes that I'm telling you here. They realized that over the years, like this thing is just not maintainable. That you want to be doing everything yourself in your database system. I like to point out Mongo because Mongo, when IPO in 2018, they had a ton of money, you had a ton of top engineers, and if they couldn't make mmap work and be functional, then what hope does everyone else have? So instead, what MongoDB did was they bought WireTiger. WireTiger only uses mmap for one very small use case, but the whole regular system is still based off buffer pools that we're talking about here today. SQLite has mmap, but it's for portability reasons, and by default, you don't get mmap. You have to tell it you want mmap. By default, you get the buffer pool stuff that we're talking about today. So this will be an overarching theme throughout the entire semester, is that the database system, meaning us actually building the system, we're always going to be in a better position to make decisions about anything and everything, right? Because we know what the queries are, we know what things we've executed in the past, what we think we're executing in the future. We know what our data looks like, what the dependencies are between them. Therefore, we're always going to make better decisions than the OS. And we'll talk about a bunch of these tricks later on, but like we'll have better prefetching than the OS, we'll have better replacement policy than the OS, we can schedule things differently. At the end of the day, we don't want to talk to the OS because it's not going to be our friend. It's always going to try to screw us over. If you don't believe me, go look up Linus's post on the mailing list about what he thinks about database people, right? He's always going to try to ruin our lives. So we never want to talk to it as much as possible. And so we actually ended up writing a paper a few years ago explicitly on this exact topic. So I'm saying it's my pet project. Because all these companies would come give talks at CMU and talk about how they're using mmap. And I was like, that seems like a bad idea. Like, oh, what are you talking about? It's great. And then like 2 years later, they were like, oh yeah, you were right. That was terrible. So we wrote a paper about it. You can go to that link there. There's a video that can summarizes the key things I'm talking about today as well. And then just a few weeks ago, somebody posted on Hacker News saying like, hey, I started building a data system using mmap because I thought I could figure it out. Nope, they were wrong. And then they were like, oh, because he knew about the paper that we wrote before. Then he realized, oh yeah, I guess I have to do what Andy said. So again, for the rest of your life, never use mmap in your data system. Okay, so if now we're responsible for memory and we're responsible for deciding what comes in and out, we have to decide what to evict when we run out of memory. Yes?
But I don't get how we bypass virtual memory. Isn't the database a user program? Does it need to use memory made available by the OS?
The statement is, how do we bypass virtual memory? I mean, yes. So when you call malloc, yes, you get anonymous mmap. The thing I care about is I don't want the OS to decide how to flush pages out. So it could start thrashing for us because we do anonymous mmap, we get a bunch of memory when you call malloc, and then it starts running out of memory, it starts paging things out. But in general, like I was saying, when the system boots up, you want to allocate all the memory you need ever at that moment, and therefore you have to tell it use exactly the amount of memory that's physically available. So if your system you're running on has 100 gigs, you would tell your data system, hey, you have 80 gigs, do whatever you want with it, and it mounts whatever it wants, and that'll never get thrashed.
But that's not true. Like if another user program asks for another 80 gigabytes, then there's going to be paging and paging.
The statement is that's not true. If another system running on the same box allocates a bunch of memory too, could you start thrashing? Yes, don't do that. That's like what else would like, you never want to run another process or another system on your database system, same machine. That's considered better, the right way to do things. If it's like a WordPress website, who cares, right? If it's something real simple. But if it's like anything mission critical, you don't run like a Bitcoin miner in the same box as your data system.
But then why would the OS want to page you out?
Why would the OS want to page you out?
If we were to use that app, why would the OS page you out if you're using little memory?
So the statement is, why would the OS page you out if you're saying that I'm running on a box that only has the memory that I need for the only thing running is my data system and has all the memory they could ever want. You're correct. It won't page you out, but it could write out the dirty pages. And that you're screwed on. As well as all the other stuff. There's other reporting issues too, like you want to say, all right, how much memory is my data system using? Well, now I gotta like go look in like whatever's in we'll talk about the page cache in a second. Like you can't just say that you can't just go to the OS and say, how much memory is this process using? Because it's like that plus the page cache or whatever mmap stuff, it becomes more complicated for reporting. Okay, all right, so good. Okay, sorry. So we have some fixed amount of memory that we can use to store data for the pages we bring into memory. But then again, at some point we're going to run out of memory, run out of free frames. You have to decide how to make space. And this is going to be called the buffer replacement policy. And the idea is that we're going to run some algorithm that can choose which page we think we're least likely going to need in the future, in the ideal scenario, and we're going to go ahead and evict it, free that frame up, and then now bring the new requested page into memory and reuse that frame. So there's this is an old problem in just computer science in general, like it's basically caching, right? Because we have to deal with that memory hierarchy where the things that have more space are going to be slower and farther away, but the fast stuff like DRAM is going to be much more limited in size. So now when we run our replacement policy algorithm, we obviously want to be correct to the extent that we can, because we want to make sure that we throw things away that we're least likely going to need in the future. And we want this to be as fast as possible, because again, if the cost of a disk I/O is like 1 millisecond, but if our replacement algorithm takes 10 milliseconds to run, we're just better off just reading things from disk. That's always going to be faster, right? And the amount of memory we're going to use to store whatever metadata we have about what's in our buffer pool, we want that to be as small as possible, because if we're spending megabytes to store again metadata about what's in the memory, then that's memory we can't be using to store more data. So, like I said, this is an old problem. One of those common solutions in systems goes back to 1965, LRU, least recently used. And the basic idea is that you just keep track of a timestamp for all the pages you have in memory based on when they were last accessed. And then when it comes time to evict something, you just pick whatever one that was accessed the longest ago. And anytime you access something again, you just update that timestamp. All right, so say I have a database that has 3 pages, and my buffer pool has 3 pages. And so again, I can just maintain this linked list here. It's one way to do it. I could do a table where the order in which they exist in the linked list corresponds to the order in which they were last accessed. Yes?
When you're keeping the timestamps, is that being stored in the metadata page tables?
This question is where would these timestamps being stored? Yeah, metadata page tables.
Okay, so you access and then you update that metadata, and then the system gives you from the memory the frame that you need.
The statement is, let me walk through this, and I think it'll make sense. But yeah, when you go try to get a page, I want to get page 1. I go look my buffer pool. I see that it exists there, so I don't have to go to disk and get it. But then I go find whatever it is in the LRU list, or it could be a table, doesn't matter, and I just move it to the front. And then I hand back the pointer to whoever wanted it. Yes?
If we have a list, then why do we need the timestamp?
The statement is, if you have a list, why do you need the timestamp? You could sort of the list, but then you got to like search the list every time. Or you have a table and could just store the timestamp in the table. effectively the same way. This is just two representations. I'll show when I show LRU-K, I'll show with a table. All right. So then now when I want to fetch something I don't memory in, right? I pick whatever's on the last page at the end of the list, and I go ahead and evict that, and then free up space for the data that I want, right? So again, this will give you the exact order in which the tables are being accessed, but maybe you actually don't need the exact order. You can do a more simplified version called clock, which came out in 1969, and it's basically an approximate LRU. And the idea is now, instead of having a timestamp or a linked list to keep track of like when things are accessed, I just have a simple reference counter that's a single bit for every single page. And then now all I need to do is check to see, has this bit been set? Meaning, has this page been accessed since the last time I checked it? Right. So at the very beginning, I would look at this one here. If I access page 1, I'll set its reference count now to 1. And then now there's this thing called the clock hand. I'm showing this in sort of a circular pattern, but obviously we store this in a list. And it's just a cursor that goes through. Anytime I want to evict something to try a free frame, I just go through and check to see whether the reference count is set to 1. If it is, then I'd put it back to 0, and I keep scanning along until I find one where the reference count is 0. Meaning, since the last time this algorithm ran, this page wasn't accessed, so therefore it's safe for me to go ahead and evict it. Yes?
You're using the word page, but to be here, are you searching the frames?
Sorry, yes. The statement is, I'm using the word page, but do I mean frames? So these are the pages that are in frames. So these are the pages that are in memory. A frame is like a memory location where I can put a page in.
So you iterate over the memory location, not the page ID.
I'd say, but am I iterating over the frame locations and not the page IDs? It's a PowerPoint diagram. It doesn't matter. But in general, like you would have the page table would be the separate thing you would iterate over that. That's separate from the frames.
Wait, no, sorry.
Yes.
That's still not here. So in the page table, you have all the possible page IDs, right? And like in certain
No, the page table is going to have what are pages that are in frames right now in memory.
It's not a mapping of page ID.
That's the page directory. The page directory is like, here's all the frames that exist. The page table says, here's the mapping from a page ID to a frame.
Right, so it has all the page IDs as keys.
That are in memory.
Okay, the list of keys changes.
Yes. Because if I evict something that
Like a hash map.
it's a hash map, but if I evict something, if I evict, going back here, I evict page 2, right? In my page table, I'll have an entry for page 2 that's going to point to a frame where page 2 exists. So now when I want to go and evict it, I would say, assuming this algorithm runs, I said, all right, I'm going to evict page 2. I remove it from the page table. So if anybody comes now looking for page 2, they're not going to see it, and they know they have a cache miss. So what's in the buffer pool, what's in the page table is whatever's in the memory right now. We'll talk about ghost pages in a second, where you could keep track of all the pages. That's not this, though. That's later. I don't want to complicate things. Other questions? Yes?
This isn't like a reference counter, it's just a bit that you
Its statement is, this is not a reference counter, it's just a bit. It's a reference count that goes up to 1. There's 1. That's it. It's not a reference counter in terms of like who's holding this page right now. It's just the same, this thing reference is accessed. Yes, the terminology maybe, it's hard to, they reuse a lot of these terms. It's called a reference bit, but it's really an access bit. Was this thing accessed since the last time I checked? All right, again, just looping through, bring in page 5, set this reference count to 0, and I keep, say these other pages are accessed. So as I scan along, I change their reference bit back to 0. I come back up here. This guy's set to 0 again. So I can go ahead and evict it. This is what basically Linux does in its own internal page table. It's a multi-hand clock. The high level idea is basically the same. Again, for some things, this is okay. Again, we're not having an exact listing, but this is probably good enough. Yes?
For each iteration of this, does the cursor resume from the index that it last evicted from, or does it start from the header?
Yes. So he said, does this algorithm resume from the beginning or where it left off last? That's where we left off last. Yes?
This only runs when we need to evict.
Yes, the statement is, and it's correct, this algorithm only runs when you need to evict something. So everything we're talking about today is like, how do you decide what to evict when I need a frame?
So like the clock's like motion, does it only start when it's saying, oh, we're accessing the query that like for page 5 that wasn't in the table? Is the clock constantly setting bits to ones and zeros, or does it only start when we're trying to access something that isn't in
It's a question, like, when does the clock actually run? So if I access a page, I set the bit to 1. I have to, right? The clock sweep only occurs when someone says, I need a frame, I don't have any free ones, then it kicks in and runs, and it starts setting them back to 0.
Why is this faster than LRU?
Question is, why is this faster than LRU? Because the amount of metadata I have to record for this is like super simple. It's a bit.
Like, does it take longer to record the current time?
So then does this take longer? Like, is the computational complexity less than LRU? Again, it depends on how you.
Because LRU can have that big list, and then eviction is just taking the last one in that list, and that's what O1.
Sure, but when I act, statement is like it's O1 to pop something off the end of the list, but when I have to update it, I got to go find it and then put it to the front again.
Yeah, that's constant time, right?
Yeah, but this is nothing. All right. I don't bring up this point yet. They bring up a very good point. This is not your algorithms class where like, oh, if it's constant time, they're all the same. No, constants matter a lot, right? Like the difference between 1 millisecond and 10 milliseconds is a lot. That's an order of magnitude. So this isn't who teaches. I don't know who teaches algorithms. This isn't algorithms. We care about that, right? So like it is constant, but like computation. It's the wall clock time is going to be significant. Yes.
Does the clock start at the same point every time?
No, the question is, where does the clock start at the same point every time? No, because in that case, you'd be hammering whatever the first one is. It's wherever you left off, right? So going back here, right? So I flip this guy, right? Say now the clock runs again. So these guys get access down below, right? Set to 1. Then I got to evict something. When it starts where it left off. All right, I don't want to spend too much time on clock. Nodism does this. It's just an approximation of LRU. LRU is actually common, but not in the simplified form that I showed before. And that's because both LRU and clock are susceptible to a problem called sequential flooding. Which basically means that if I have a query that comes along and does a sequential scan, which means I'm going to read the table from beginning to end, then that's going to blow away any recency information that I've been maintaining in my database system for these pages, because it's going to go through and rip out, throw away things, and put a bunch of pages into my buffer pool that maybe I actually don't want to be in there, because I only need it for that sequential scan. So I lose all sort of the information that I have about, again, the recency information. You're basically polluting the buffer pool. And in some workloads, like OLAP for analytics, we'll talk about that next week, where you're not really doing single lookups on single keys. You're actually doing these scans over and over again. And you don't actually want least recently used. You actually want most recently used. Because then you start playing games of like, oh, I do much sequential scans, so I'll scan from beginning to the end. Next query shows up. Maybe I want to scan from the end to the beginning, because the pages that I just read are going to be in the buffer pool. Right? So what is sequential flooding? It looks like this. So say I have a query at the top. I'm doing it's called a point query. Where, I'm trying to find a single record where ID equals 1, assuming ID is the primary key. So somehow I figured out that ID equals 1 is in page 0. So I go ahead and put that in my buffer pool. Then now a scan query comes along. I want to compute the average from some column in the table, and that's going to go from beginning to end. And at some point, it's going to run, when it gets to this last page here, page 3, it doesn't have any more free space in the buffer pool. So then it's got to run the LRU algorithm to decide what to kick out. Well, page 0 was the last thing that it read, the one that's least recently read. And I'm going to go ahead and evict that and put it in page 3. But let's say this query at the top where I'm doing these ID lookups, that's actually super common. And I'm doing a bunch of lookups on this ID equals 1. Like workloads are very skewed, where people are always trying to read the same thing or write the same thing over and over. Thinking like, Taylor Swift's, she's on Instagram, whatever, her Instagram account versus like some random guy's cat's Instagram account. There's more people reading Taylor Swift's thing rather than the cat guy's thing. So we want to keep the Taylor Swift thing in memory. But if we're just using LRU, we wouldn't be able to do that because we would not know that Taylor Swift is popular, and we would end up evicting her page if we used that basic LRU algorithm, right? So you say, all right, well, what if I do something like keep track of how often these pages are being used? And there, when I want to run my eviction algorithm, I want to do the one that has been the least frequently accessed, right? Just maintain a counter for every single page of how often they're being accessed and when they're in memory. And then now when I want to evict something, it's pick whatever one that has the smallest count, right? Seems reasonable. Of course, there's a paper on this from 1971, 2 years after clock. Well, this causes more problems because now, to his point about the complexity, now it's logarithmic complexity maintaining this information, all right, because for all the table. And then furthermore, if I have someone that does something weird, like go look up the cat guy's Instagram account in the middle of the night 1 billion times, and then at no point does everyone go back and look at that cat guy's account, his counter is going to be super high. I'm never going to end up evicting it, even though it's not useful anymore at all. Because there's no information about time in this count. It's just like how many times was it accessed. Now, how long ago was it accessed? So the solution to this is a simple enhancement that came out in the early 90s called LRU-K. And there's a great paper that talks about this. And this is actually what's used in SQL Server. This is actually what Postgres implemented first in the late 90s, written by this guy, Tom Lane, he did his PhD here at CMU. And the basic idea is that we're going to maintain multiple LRU lists. And then when it comes time to evict something, we're going to calculate the length of time from when it was last accessed, or the oldest access, and the current time. And then that way we can decide who has been accessed the longest ago. And since now we're going to have these multiple LRU lists, we would know whether someone just accessed something once and never accessed it again. And so therefore we don't have that blowout before where someone has a high count that never comes back. So in order to make sure that if we evict something and then bring it back in, we don't have to learn from scratch all over again that this thing is a hot page or not, we can actually also maintain what are called ghost caches or ghost lists, where we can keep track of, even though something got evicted, we'll still keep in memory its access timestamps, so that when we go fetch it back in the second time around, that we can pre-populate our LRU lists or timestamps with what it was before it got written out the disk. So again, this now provides more persistence into our algorithms so that if we write things out, again, we're not just learning from scratch all over again. So let's look at a simple example. So now instead of using an LRU, a linked list to keep track of the ordering, I'm going to maintain this separate table, right? And you can think of this as like the page table where I'm just maintaining timestamps of things. So say that in the past I've accessed pages 0, 1, and 2, and that's what's in my buffer pool. And assume the timestamp is just a monotonically increasing counter, like a 32-bit integer, right? 1, 2, 3, 4, 5, 6, so forth. So the query starts off here. I have an in clause where I'm going to access 4 different values on 4 different pages. Now I'm going to show this in sort of the order that they're specified in the in clause. But again, SQL is unordered. So in actuality, you would actually want the system to figure out what pages these records are on, like 131, 11, and 41, and then do them in sequential order. But for simplicity, or to show how the page history works, I'm going to have them jump around randomly. So when my query starts off, I want to read ID equals 1. That's in page 0. So now, because I already have this entry in my buffer pool, I'm going to have the 2 columns. One is going to be the last access, the most recent one, and then the second access, since we're doing k equals 2 here, I'll have a second list and keep track of like the oldest timestamp for this. So at the very beginning, if I access it once, there's nothing in that sort of second column. And again, I'm showing k equals 2. You can go up to k equals 6. Some systems can do that. All right, so in this case here, because now I'm going to access it at timestamp 4, 1 gets slid over to the other column, and then I'm put timestamp 4 here. Then now I jump down to access page 3. All right, so now this is not in memory in our page table. So we got to decide what we want to evict to free up space to put it in memory. So the eviction policy is going to take whatever the current timestamp is for us. Again, that's just a counter increasing. And then we look at the oldest last access timestamp, right, with the kth one. So in this case, k equals 2. We'll look at the last access number 2 column. And we'll just subtract that to figure out what the distance is between the two accesses. And then choose whatever one is the largest, meaning it's been the longest since it was last accessed before. If you don't have an entry in the second column, you just use infinity, right? And if you have ties, you just pick whatever one that has the oldest timestamp. So again, we're gonna look at the second column here. We just go through, take the current timestamp 5, subtract it by whatever's in the second column. In this case here, because it's time 5, subtracted by 1, you get 4. But then the other two guys don't have entries there, so it's infinity. So then now I would say, all right, well, both of these are infinity. I'm gonna pick whatever one has the smallest timestamp, the oldest timestamp, in the first column. In this case here, it'll be page 1. We go ahead and evict that and put that in, and then we update it to page 5. Do it again. So now if I access page 1, that's the thing I just evicted, so it's not in memory. So I got to do that same algorithm that before, where I just subtract whatever the timestamp is with the last access one. In this case here, the two bottom ones are still infinity. I pick page 2 because this timestamp is 3 is less than 5. So that's where I'm going to go ahead and evict it. So that's where I'll put page 1. But now again, remember, I can say I can have that ghost list or ghost cache where I keep track of the timestamps of pages I just evicted. So I just evicted page 1 from 4. So I can go ahead, if I have the ghost cache, I can put timestamp 2 in there. And that way, if the eviction policy runs again, this doesn't end up getting thrown out immediately all over again. I access the last page, page 4. Again, run the same algorithm, run the same calculation. Now I get this middle guy here because he hasn't been accessed twice. I'm going to go ahead and evict page 3 and put page 4 in there. Yes?
So is that ghost cache information not part of the page table, and that's like a separate memory allocation?
The question is the ghost hash part of the page table, or is that a separate data structure? It's usually a separate data structure. It's not that big, so it's not a big deal. Yes?
For the timestamp, when you're using the integers and you add up 1 each time, is that the way it used in real application?
The question is this timestamp, I'm showing this as it's a logical counter. Would you do that in a real system, or would you use like hardware clocks, like the wall clock time? You typically would use a logical one, because the wall clock time can change when there's like if you like daylight savings and things like that. Time can go backwards. That's gonna be a bigger problem when we talk about transactions later on. How to deal with that? Yeah. Oh, time is terrible. Yeah. Other questions? Okay, so let me show a sort of simplified version that MySQL uses called approximate LRU-K. And the basic idea is that they're still going to have one linked list. And again, it could be a table, it could be a linked list, it doesn't matter. But they're going to partition it into young and old regions. And you're going to have 2 entry points into the linked list that allow you to find the beginning of the old region and the beginning of the new region, the young region. So now when I access a page, say accessing page 1 here, I got to evict something because it's not my buffer pool. So I'll pick whatever is, I'll go into the old list, slide everything over by 1. So I'm going to get rid of page 8. These guys slide over, and that's where I'm going to put page 1 in. And the reason I'm going to put it in the old list rather than all the way at the beginning there is because if I never access this page 1 again, then it'll just get sloughed off at the end, right? No big deal. But if I do now access page 1 again, then what I want to do is now put it at the beginning of the young list, because I'm saying, oh, this is clearly important because it keeps getting access again. So let me go improve its chance not to get evicted very soon while putting it to the front of the young list. Right? Again, it's approximate. It's not exactly the way LRU-K did it, but it kind of gives you the roughly the same benefit. All right, I want to talk. We're short on time, but I do want to talk about this ARC one because this is what you have to implement in project 1. And as I said, the projects this year are harder than the previous years because you can, by all means, use LLMs to help you code. So this is called the adapter replacement cache. It was invented by IBM Research, actually for their disk storage systems, but I think it went into IBM DB2. It's in ZFS as well. And it actually was in Postgres, was added in Postgres 2004 or 5. But IBM patented this, and the Postgres people were kind of worried about that. So they made some little tweaks to the algorithm to make it look less like the patent, although IBM hasn't enforced it. And actually, I think it expires next year. But this is roughly considered this kind of policy or the kind of algorithm is roughly considered the state of the art for buffer replacement algorithm. But the basic idea is that we want to get all the benefit of something like least recently used, as well as the benefit of least frequently used. But instead of having to maintain sort of separate lists, instead of having to balance how much we're going to depend on one list versus the other, and you have to manually tune that, we instead want to have this sort of built-in policy that decides how to size up the different lists based on the access patterns of the query. And then, of course, we're going to maintain a ghost list to keep track of what things been evicted recently, so that if we go fetch them back in, we can record that history and rely on that. So, in the sake of time, I mean, I know we need this for the project, but we can follow up online to do a recitation of this separately. But basically, there's these multiple lists we're going to maintain. There's this parameter P where we keep track of how much we want to favor putting things in the least recently used list, the recent list, or the frequent list. And so we find ourselves accessing the same things over and over again, then we'll allow the size of the pages we're tracking in the frequent list to grow and correspondingly shrink the recent list. So you sort of automatically get the best of both worlds of both least recently used and least frequently used. And it can eventually narrow in exactly what the workload actually wants. And because it's dynamic, if the workload changes over time and the access pattern changes over time, this thing can handle it. So again, we'll follow up and do a separate recitation on the algorithm because you'll need it for the project. And there's a lot of videos online that discuss how this works. But it's basically the same concepts we had before. Again, except you have this P parameter that changes where things are going to go. Okay. All right. Other tricks you can do to make things go better is to have information about how the page is actually going to be used. Like if I know that I'm doing a query, scanning a table for sequential scan, and it's unlikely that this table is going to be used by other queries, then I don't want to put it into my global buffer pool. I want to have a little separate side cache or a separate portion of the buffer pool that's dedicated just for my one query that's running. So then now as I'm scanning through, I'm not putting things in the global buffer pool and having that run its own eviction policy. I'm putting this in my own little buffer pool on the side, but it's really just a partition piece of the total amount of memory that's available for the system. So Postgres does this, and they basically maintain a circular ring buffer for some portion of the buffer pool, so that every time I ask for a new page, I'm just appending to the end, and then eventually it'll wrap back around. So it's really cheap to actually implement. And again, you minimize the effect of sequential scans or sequential flooding on the rest of the system. Another trick you can do is maintain priority hints to about how the query is going to act, or how the execution is using this data, and what's actually in the pages, so that when the buffer pool replacement algorithm runs, it knows to avoid pages that it somehow thinks are more important than other pages. So think of something like I have an index. We haven't talked about B plus trees yet, but assume it's a tree data structure. And so I would have priority hints for my pages that say the top of the index, the first page, that's super important because that's where everyone has to go to in order to get inside the data structure and figure out where they need to go, right? So think of like, this is not valid SQL, but assume I'm inserting values where I'm just incrementing some counter by 1 over and over again, right? Well, if I'm sorted along from min value to max value along the bottom on like my leaf nodes, then anytime I want to insert something, I always got to go to the root, and I'm then always going to go down on this side of the tree. So therefore, I should tell my data system, hey, that the index page 0, that's super important. Yes, I would see that it's being accessed all the time as part of my frequency information, but maybe I want to just make sure that the data system, no matter what, never pages it out. Because the first thing I'm always going to do if I want to access the index is always go to that root. And same thing if I want to do a lookup. There's other tricks you can do about priorities, like if I know that there's a transaction that's running multiple queries, and the first thing it does is read some record and then immediately update that record. I don't want to I don't want the that to look like two separate unique accesses to my buffer pool manager, I want to tell it, oh, by the way, this is part of the same transaction. Therefore, it only updates like the access counter once. Because it didn't become more popular because everyone's trying to access it. It's just one transaction trying to access it multiple times. So SQL Server can do stuff like that. So again, so there's a bunch of hints and a bunch of information we can provide to the buffer pool manager based on how we know queries are accessing this data. And I didn't say this at the beginning, but I'll say it. I'll say this multiple times throughout the semester. This is one of the things that's going to separate the expensive enterprise systems, like the Oracles, DB2s, the Teradatas, from the open source systems like Postgres, MySQL, and SQLite. Like they're going to have to spend a lot more time and more money to make these buffer pool replacement algorithms as sophisticated as possible. Like the ARC thing is in IBM, and that paper came out and the Postgres guys implemented it, but it's not public. But there's a bunch more things they've added since then in the DB2 version. All right, so what happens now if we want to evict a page, and we identified this one we want to remove, but it's been marked dirty, meaning some part of the system has modified the changes since it was brought into memory, and therefore we can't just throw it away. We have to go write it back out the disk before we can reuse the frame. So if the page has not been modified, then it's super easy for us because again, we just drop the memory, no big deal. If it has been modified, then in order for us to use that frame, we have to wait until we write that data out the disk. It gets flushed. In some cases, we have to write out another record, another page that tells us about what was modified in that page, like a log record. We have to flush that page, then we flush the other page before we can free that frame up. And that's obviously going to be slow for us. So what we want ideally is when our buffer pool replacement algorithm runs, we only want to consider free pages. And so the more clean pages, the more clean pages that we have, the better chance we have of finding one that will be least likely to be used in the future. So similar to how the OS can do that preemptive background writing for pages in mmap, the database system can do the same thing. Again, this is you're just walking through the page table, finding any pages that are marked as dirty, and going ahead and writing them out in a background thread. So then the idea, again, by the time someone wants to go free that frame, the dirty data has been written out, and we don't have to block and wait for ourselves. This is sometimes called page cleaning or buffer flushing. The basic idea is the same thing, right? And then once we've written out the dirty page, we can go flip the dirty bit, and then it can be evicted easily. Of course, now the challenge is going to be if we spend all our time doing background writing, that's going to slow our system down because now all our I/O is flushing out dirty pages when we could be using it for running other queries. So again, the high-end enterprise systems have all sorts of thresholds and other backup mechanisms you can put in place to say how aggressive you want it to be on background writing, where other systems might just run it on a periodically on a schedule, or if so many pages have been modified. Like I think Postgres, it'll do background writing if 30 pages in memory have been modified, then it kicks in. Like there's simple things you can do like that, but the commercial systems are more sophisticated. All right, so let me try to get through disk I/O quickly, and then we can pick back up on the optimizations you can have in your buffer pool next class. So when we have to write pages out the disk or read pages from disk, we want to do it in such a way that we can maximize the throughput or the bandwidth of the hardware, so that again that we can, for a certain amount of fetches and a certain amount of time, we can get as much data as we can from disk into memory. Disks have gotten a lot faster in recent years, but it still is a pretty significant bottleneck. So the way the operating system and hardware is going to try to do this on modern systems like NVMe drives is they want to maximize the amount of parallelism. And they try to be clever about reordering I/O requests to make sure things are done in sort of maximize the amount of sequential ordering, right? But the challenge is that it doesn't know which of these requests have a higher priority than other requests because it doesn't see that information, right? So you can set the I/O priority for doing disk reads and disk writes, but you can only do it at the process level in Linux. So if our single database system has 2 threads that want to read data, one is for a mission critical query and one's for like a background thing, who cares if it's slow, Linux doesn't know anything about those 2 requests. So this is, again, why we want to do all the scheduling in our own system. And a lot of these systems will just tell you turn off any kind of sophisticated scheduling information or scheduling policies in Linux. Go do the most simplest thing because we're going to do everything better ourselves inside of our database system, right? And basically the way this works is that the database system maintains its own internal queue of the I/O requests that are coming from up above from the buffer pool manager, and then it can reorder things based on how those queries are accessing the data based on what it knows is the important things to consider. Like, again, most simple thing with sequential I/O versus random I/O. If I have a bunch of requests for from random pages from multiple workers or multiple threads, then I can just look at all the requests, sort them by the page ID or the location on disk, and that way I can turn all these random I/Os into a sequential I/O. If it's a part of a query or a transaction that's important, I want to prioritize those versus random background tasks. If I know I'm writing out log data, that's really important to write that out first to make sure things are durable before I write out maybe like other random dirty pages. There's a whole bunch of things we can consider that the data system simply is not going to, the OS is not going to know about because it doesn't know what's inside of our application or system that's actually running. I keep saying application because then from the OS perspective, the data system is just another application. So I don't mean like your Node.js application over there, but from the OS perspective, the data system is another application. So that's what I mean by that. But I really mean our system we're actually building. The OS doesn't know any of this, and it's just going to make things harder for us. And so we want to try to avoid that as much as possible. Another thing we got to be mindful about is the OS page cache. So when I call fread or read using the libc posix syscall, that's going to go into the kernel, into the file system that's running in the kernel. And then it's going to consult its internal page cache in the OS. And if it's not in the page cache, then it goes down the disk, copies it into the page cache, and then copies that again to a user space buffer that goes up to our data system up above, right? But now if I'm maintaining my own buffer pool manager, that's another copy of pages that are out on disk. So that's actually two copies now that are in memory in our OS or in our system. So you have one copy of a page in the OS page cache, another copy up in user space in our database system. That's super wasteful. We don't want that. So instead, you can use what's called direct I/O, where you basically tell the file system, don't put it in your page cache, bypass all that, go directly to the hardware, get what you want, and then hand me back the memory buffer for it. And that avoids that additional copy. Things are much, much faster. There's actually other optimizations you can do called using DBDK, data plane data kit. We'll cover this in the advanced class. You can basically have the data system talk directly to the hardware and not go through the file system at all and get data out. So most data systems will run with direct I/O. There's one system that's widely used that doesn't use direct I/O. Anyone know which one it is? SQLite. No, I think you can run with direct I/O with those guys. It might be on by default too. It's Postgres, right? Postgres, famously, because it's like some relic of the 1980s, relies on the OS page cache. Every other data system out there tells you, as I said before, like if you have 100 gigs, use 80% of the memory for the buffer pool in your database system. Postgres says use 25% because they want the other remaining memory to be used for the OS. But then this has all sorts of problems, all sorts of performance issues, because again, you're maintaining multiple copies of data, and it's wasteful. So Postgres has been trying to get off OS page cache and switch to direct I/O for many, many years. This is a LinkedIn post from last year talking about how they have patches for this. And then coming out in 2 weeks is Postgres 18. This I don't think has direct I/O on by default, but it's now going to have asynchronous I/O. So now I can have separate background threads in Postgres or processes in Postgres. Go retrieve data from disk. It's still going to use the OS page cache, but I don't have to block the rest of the system while I'm doing that. Because you need to have asynchronous I/O before you can do direct I/O, because direct I/O is going to be slower because you're never going to really hit the OS page cache. Yes?
You have to make changes in kernel, or does the database do it during installation?
The question is, do you have to make changes in the kernel to do what? Direct I/O? Yeah. No. Direct I/O is like a POSIX command. Like when you call fopen, you just say you pass in odirect, right? By default, that's not that. Yeah, you don't make any changes to the kernel. All right. Bottom line is this is coming in Postgres. They're going to get off of OS page cache very soon. And there's, again, the OS is always going to cause problems for us. All right, I want to finish up with this last example here. And again, just I know I sound crazy up here saying the OS is our enemy and we don't want to talk to it. Let me show why. All right, so say I have a dirty page in my buffer pool, and I got to write it out to disk. I call fwrite. What happens?
Until you did it.
What's that? I heard. Say it again. Say it again. What are you saying? Sorry. Say it again. Sorry. Oh, writes to a file. Sorry. Okay. I thought you said get arrested by 5. All right. Sorry. Writes to the file, but like where? See, they say on the disk.
Depends on if you flushed or not.
Depends on when you flush. We're not flushing yet. So it sits in a kernel buffer, right? To his point, if I really want to get it to the hardware, I got to call fsync. That's another POSIX command. It's a blocking call where you tell the OS, make sure this thing is actually written to the hardware. Now, the hardware can play games and lie to you too, right? Because the hardware can have its own battery down there where you do fsync, it writes to the battery backed RAM or storage, and then it's not really on the actual storage medium yet. But in a rare case, you lose power, then the battery can then do the final write. But when I call fsync, I block until I get a notification saying my flush has succeeded. But if fsync fails, what happens? Well, Linux in the old days would mark the dirty pages as clean. Because I have a bunch of dirty pages that modified with fwrite. OS keep track of them. I call fsync. It wants to write out the dirty pages, and then wants to mark them as clean, and it marks them as clean, and then notifies you that fsync is completed. But if fsync fails for whatever reason, because the hardware fails or flipped out or something, it comes back and you get a failure notification. You get a failure error number. But then the OS marks those pages, dirty pages, as now clean. So the problem was a bunch of database systems would do fsync in a while loop. While fsync fails, try again. So the first time you call fsync, it would fail. It would loop back around, then try it again. But since the OS, Linux, would mark the page table was clean the last time you called fsync, even though it didn't work, when you call fsync the second time, it says, oh, yeah, you're good, done. And it looked like it would succeed. So why would it do this? Why would Linux do, again, they fixed this, but why did they used to do this? Because Linux wasn't worried about the database system, even though it's the most important thing in the world. They were worried about some asshole with a thumb drive pulling out the thumb drive, and then now you have a bunch of page in your page table from a thumb drive that's never going to come back. So they would mark it as clean so that they can clean it up later on, right? But it was lying to us in the database system that our page was actually written, even though it actually wasn't. So some guy on the Postgres mailing list posted this like 2018 or 2017. He's like, hey, look, I think Postgres lost some data for me, and I didn't have a kernel panic. I didn't have a disk crash. It was a silent error. Some guy started reading through the code in both Postgres and Linux, and turns out, Linux was lying to us for 20 years. And it wasn't just Postgres. MySQL had this problem. I think MongoDB or WiredTiger had the same problem. So I'm going to put this up for multiple times a semester. Don't do this, right? Don't call fsync again. Assume everything's going to be okay, because the OS is going to lie to you. So this was a big scandal. It was called fsync gate. This has since been fixed in Linux and also been fixed in Postgres and MySQL and MongoDB. But this is a good example. The OS is going to make, read the documentation. It's going to say one thing. It's actually do something different. So therefore, we have to be super protective and make sure that we don't put anything that could fail will fail. And we have to do more extra stuff in our database system to make sure that we don't lose data. Okay? All right, we're over time. Apologize. We'll pick up on this next class. And then post everything on, it'll be posted on Piazza. And we'll post Project 1 later today. Hit it.
Cash money, click, flips, acrobats over tracks. 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 Get the fortune, motherfucker fame. Maintain but never strain
Get the fortune, motherfucking fame. Maintain but never strain flow with the